In this video, we are going to discuss how to calculate electric field at a point due to a conducting spherical shell using Gauss's law. Question 2.55. A 6 nanocoulomb point charge is located at the center of a conducting spherical shell. So we call this charge as Q, and magnitude of Q is negative 6 nanocoulomb. The shell has an inner radius of 2 meter. So this is my inner radius. We call this R1, and an outer radius of 4 meter. We call this R2, and a charge of 7 nanocoulomb. So the charge on the shell is 7 nanocoulomb. In part A of the question, we need to find what is electric field at R equal 1 meter. So we need to find what is electric field at this point, a distance R from the center. Since we are going to use Gauss's law to solve this problem, we will first construct a Gaussian surface passing through the point a distance r from the center. So here we construct a spherical Gaussian surface, and I'm going to find what is the electric field at this point because of the whole system. According to Gauss's law, the total flux through a surface is equal to the charge enclosed by the surface over epsilon naught. The flux through any closed surface is given as integral E dot dA. The double integral sign here because the area vector is two-dimensional, and the circle over the integral sign means that we are taking this integration over a closed surface. Since electric field through the surface is going to be constant, we can take E out of the integral, and then we take integral dA equals charge enclosed over epsilon naught. Now, since my Gaussian surface is spherical, its surface area A will be 4 pi r squared, where r is the radius of the Gaussian surface, whereas the charge enclosed by the Gaussian surface is Q, where the value of Q is negative 6 nanocoulomb. So I will substitute this in my expression for flux. We will write phi equals E integral dA will be 4 pi r squared equals charge enclosed is just Q over epsilon naught. You can either put the negative sign of Q here, or you can put the negative when you substitute this value. I'm going to put the minus sign when I'm substituting the value for Q. So now rearrange to write for E. You get E equals Q over, we divide by 4 pi r squared epsilon naught. We know that K, which is the Coulomb constant, is equal to 1 over 4 pi epsilon naught. So we can substitute 1 over 4 pi epsilon naught here as K. Therefore, that gives me electric field to be equal to KQ over R squared, which is nothing but the electric field due to a point charge. Now we can substitute our values. K is 9 times 10 to the power 9. Charge Q is negative 6 nanocoulomb. The distance R here is 1 meter, so 1 squared. And when you solve this, you get electric field at a distance 1 meter from the center to be equal to negative 54 Newton per coulomb. The only reason we have electric field in the hollow region between the spherical shell is because there is a charge Q present at the center. If this charge was not present in the center, electric field at a distance within the hollow region of the shell would have been equal to 0. But since we have negative Q present here, this is the magnitude of my electric field at a distance r equals 1 meter from the center. Now let's discuss part B. In part B, we need to find what is electric field at r equal 3 meter. Now 3 meter is between 2 and 4 meter. That means this point lies within the conducting shell. And we are going to follow the same step to calculate electric field at this point. So let us construct our spherical Gaussian surface within the conducting shell. We know that electric field inside a conductor has to be zero because even though there is a charge present in the center, this charge will induce an opposite charge on the inner surface of the shell. So if I have negative Q here, it will induce a positive Q on the inner surface of the shell. So that will neutralize the effect of the charge at the center, whereas the charge within the shell will arrange themselves on the outer surface of the shell, creating a net electric field of zero inside the shell. So at any point inside a conducting shell, electric field has to be equal to zero. Next, we look at part C. In part C, we need to find electric field at a distance r equal 5 meter. So this distance lies outside of the spherical shell. We will construct a Gaussian surface passing through the point at a distance 5 meter from the center. And we follow the same steps to calculate electric field. I write my total flux through the surface will be equal to charge enclosed over epsilon naught. By the definition of flux, we can write the flux phi to be equal to integral over the closed surface E dot dA equals charged enclosed over epsilon naught. Again, E is constant, so we take it outside of integral. dA equals charge enclosed over epsilon naught. This area is the area of the Gaussian surface. And right now my Gaussian surface is at a distance r from the center. And area of a sphere is given as 4 pi r squared. Charged enclosed is the total charge enclosed by the Gaussian surface. So here we have two charges within the Gaussian surface, the charge of the shell and the negative charge at the center of the shell. So we write charge enclosed to be equal to Q of shell plus Q at the center. Again, the minus sign of Q I will take when I'm substituting the value. So you have to take the minus sign only one time. Either you write this as negative Q here and don't take the negative sign later, or you can just put this as plus Q and take the negative sign when you're substituting the value. Now let's rewrite this expression for phi. I write E into 4 pi r squared equals charge on the shell plus charge in the center over epsilon naught. Divide by 4 pi r squared to calculate E. Q shell plus Q over 4 pi r squared epsilon naught. Again, 1 over 4 pi epsilon naught we will take as K, and we will substitute that as 9 times 10 to the power 9. So let us substitute the values and calculate E. Charge on the shell is 7 nanocoulomb, so 7 times 10 to the power negative 9, plus charge on the center is negative 6 nanocoulomb. And this multiplied with K, which is 9 times 10 to the power 9. Again, 1 over 4 pi epsilon naught I'm taking as K over R squared. So R here is 5 squared. And when you solve this, you get electric field at a distance of 5 meter from the center to be equal to 0.3597 Newton per coulomb. So this is how you can use Gauss's law to find electric field at any point due to a conducting spherical shell. Now let's discuss part B. Part A is asking us what is the surface charge distribution sigma on the outside surface of the shell. Here we have a charge negative Q at the center of the shell. And this charge is going to induce an opposite charge on the inner side of the shell. So if this is negative, on the inner side, you will have a charge of positive Q. And the total charge on the shell has to be a sum of the charge on the inner surface plus the charge on the outer surface. So if I want to find the charge distribution on the outer surface, I need to calculate what is the charge on the outer surface, which is QO. So we can rearrange this term to write QO as charge on the shell minus charge on the inner surface of the shell. Now charge on the inner surface of the shell is same in magnitude but opposite in sign as the charge in the center. So Qi will be equal to minus of Q, which is equal to plus Q. So it will have same magnitude or the same size as the charge in the center, but opposite sign. So I will write Qi as 6 nanocoulomb. I need to find the surface charge distribution. Surface charge distribution on the outer surface will be equal to charge on the outer surface over the area. So charge on the outer surface is charge on the shell minus charge on the inner surface over the area. So area of the outer surface we will have to take as 4 pi r2 squared, as r2 is the radius of the outer surface of the spherical shell. Now we can substitute the value. Charge on the shell is 7 nanocoulomb. Charge on the inner surface of the shell is 6 nanocoulomb. Divide by the area, 4 pi r2 squared. That gives me 1 nanocoulomb over 4 pi r squared. So 1 nanocoulomb is 1 times 10 to the power negative 9 over 4 pi r2 is 4 squared. And when you solve this, you get the surface charge distribution to be equal to 4.97 times 10 to the power negative 12 coulomb per meter squared.